Section: Introduction. In this section, we discuss how real-world enterprise data, such as financial transactions and customer interactions, is mainly stored in relational databases. These databases consist of multiple tables for different types of entities, linked through primary and foreign keys. This structure holds vast amounts of complex data that can grow with business needs, but extracting useful insights has often required manual feature engineering, transforming multi-table records into simpler formats for machine learning models. To facilitate deep learning, we can represent relational databases as relational entity graphs, where nodes represent entities and edges show the relationships between them. This allows graph neural networks, GNNs, to learn features directly from the data structure, reducing the need for manual feature engineering and often improving performance at a lower cost. However, standard GNNs have limitations, such as not being able to effectively model long-range dependencies. For instance, in an e-commerce database with customers, transactions, and products, transactions are only connected through customers, creating an information bottleneck. This means that understanding transaction patterns requires multiple layers of message passing, and product relationships are only indirectly captured. Graph transformers, GTs, have been developed to address these issues by using self-attention to enhance information flow and incorporating positional and structural encodings. While GTs have shown strong results in various domains, many designs are not suitable for relational entity graphs, which are often heterogeneous, temporal, and large-scale. Existing positional encodings can be costly to compute and do not scale well for complex relational structures. To tackle these challenges, we introduce the Relational Graph Transformer, RELGT, specifically designed for relational entity graphs. RELGT effectively captures the unique characteristics of relational graphs within the relational deep learning framework. Our architecture includes a multi-element tokenization scheme that enriches each node with detailed information without requiring expensive precomputation. We also develop a transformer network that balances local and global representations, allowing the model to learn from both detailed node features and broader patterns. We validate RELGT's effectiveness through extensive testing on 21 tasks, showing that it consistently outperforms GNN baselines, achieving significant improvements without additional computational costs. In summary, we highlight the advancements in RDL methods, including the baseline GNN approach that uses a heterogeneous graph SAGE model, which has shown notable improvements over traditional methods. Various specialized architectures have been created to address specific challenges in relational entity graphs, confirming the effectiveness of combining graph, tabular, and LLM-based methods for predictions in relational databases. However, these methods often focus on narrow aspects of the problem and do not fully leverage the broader advancements in graph learning. Section Summary. In this section, we discuss the challenges of extracting predictive patterns from relational databases, which traditionally rely on manual feature engineering. We introduce the Relational Graph Transformer, RELGT, a novel model designed to effectively learn from relational entity graphs by capturing their inherent complexity, outperforming existing methods in relational deep learning tasks. Section: Graph Transformers. In this section, we discuss graph transformers, which enhance the self-attention mechanism used in sequence modeling to work with graph-structured data, providing strong alternatives to traditional graph neural networks, GNNs. These models usually focus attention on local neighborhoods, acting as message-passing networks that aggregate information based on attention, while positional encodings are created using Laplacian eigenvectors. Later versions of graph transformers introduced global attention mechanisms, enabling all nodes to interact with each other, thus overcoming the local limitations of standard GNNs, although this increases computational complexity. Modern graph transformer architectures have built on earlier work by developing effective structural encodings and ensuring they can scale to medium and large graphs. To enhance the structural expressiveness of node tokens, various positional and structural encoding methods have been created to incorporate the input graph's topology. For scalability, we have seen strategies like hierarchical clustering to simplify graphs, sparse attention mechanisms to cut down on computational costs, and neighborhood sampling techniques for handling large graphs. Models such as Graph GPS merge these advancements through hybrid designs that maintain the global context benefits of transformers while ensuring efficiency for medium and large datasets. However, these methods have notable limitations. They mainly apply to static graphs and struggle with multiple types of nodes and edges. While there are specialized transformers for heterogeneous graphs, integrating them with other methods into the relational data learning (RDL) pipeline is challenging. This is mainly due to the difficulties in adapting positional encodings under precomputation constraints and the complexity of modeling large-scale, temporal, and heterogeneous relational entity graphs. Next, we address tokenization. Traditional transformers in natural language processing represent text using tokens that consist of two main elements: token identifiers, which indicate the token from a vocabulary, and positional encodings, which show the sequence structure. For instance, a token might represent a word, while its positional encoding indicates its order in a sentence. Similarly, graph transformers adapt this two-element representation for graphs, where nodes act as tokens with features, and graph positional encodings provide structural information. While this approach works well for homogeneous static graphs, it becomes inefficient when trying to encode various aspects of graph structure for relational entity graphs. Specifically, capturing heterogeneity, temporality, and schema-defined structure through a single positional encoding would either require complex multi-stage encoding or lead to significant information loss. For example, extending existing positional encodings for relational entity graphs presents several challenges. Standard Laplacian or random walk-based encodings would need major adjustments to distinguish between different node types, such as customers, products, and transactions. These encodings do not account for temporal dynamics crucial for time-sensitive predictions. And the scale of relational databases makes global positional encoding computation prohibitively expensive, as precomputation would only be feasible on small subgraphs, leading to incomplete structural context. Our proposed approach, RELGT, addresses these limitations by using a multi-element token representation that does not add computational overhead based on the number of nodes in the input relational entity graph. Instead of compressing all structural information into a single positional encoding, we break down the token representation into distinct elements that explicitly model different aspects of relational data. This design allows each component to capture specific characteristics. Node features represent entity attributes. Node types encode table-based heterogeneity. Hop distance maintains relative distances among nodes. Time encodings reflect temporal dynamics, and GNN-based positional encodings preserve local graph structure. In the tokenization process of RELGT, we convert a relational entity graph into sets of tokens suitable for processing by the transformer network. For each training seed node, we sample a fixed number of neighboring nodes from within 2 hops of the local neighborhood, ensuring that only nodes with timestamps less than or equal to the seed node's timestamp are included to avoid temporal leakage. Each token is represented by a 5-part structure that includes node features, node type, relative hop distance, relative time, and a graph positional encoding generated by applying a lightweight GNN to the subgraph's adjacency matrix. Each element in this 5-part structure is processed by a specialized encoder before being combined into the final token representation. The node feature encoder transforms the raw features into a multidimensional embedding, while the node type encoder converts each entity type into a representation that captures heterogeneous information. The hop encoder encodes the relative hop distance into a multidimensional embedding, and the time encoder transforms the time difference between nodes. Finally, the subgraph positional encoding captures local graph structure through a lightweight GNN, which preserves important relationships among entities. One advantage of using random node features in this GNN encoder is that it breaks structural symmetries, enhancing the expressive power of GNN layers. However, to maintain permutation equivariance, we resample the random features independently at each training step. This stochastic initialization approach helps preserve the benefits of randomization while ensuring generalization. Ultimately, We form the effective token representation by combining all encoded elements, resulting in a comprehensive representation that captures node features, type information, structural position, temporal dynamics, and local topology without incurring high computational costs. Section Summary. In this section, we discuss graph transformers, which adapt self-attention mechanisms for graph-structured data, allowing for both local and global attention while addressing scalability and structural expressiveness through multi-element token representations. Our proposed approach, RELGT, enhances tokenization by decomposing representations into distinct elements that capture various aspects of relational data, enabling efficient processing of complex relational entity graphs without incurring significant computational overhead. Section: Transformer Network. In this section, we describe the transformer network used in RELGT, which processes the tokenized relational entity graph through local and global attention mechanisms, inspired by successful designs in modern graph transformers. For the local module, we utilize a local attention mechanism that allows each seed node to focus on its selected local tokens, capturing detailed relationships defined by the database schema. This approach differs from traditional graph neural networks in two main ways. We employ self-attention for message passing, and all nodes in the local set interact with each other. We implement this using a multi-layer transformer network, which enhances structural coverage compared to a baseline graph neural network. An example of this improvement is seen in e-commerce, where our attention mechanism connects seemingly unrelated products by identifying relationships through shared transactions or customer behaviors, allowing us to capture subtle associations, like unexpected item combinations frequently purchased together. The local node representation is derived from multiple layers of the transformer, where standard components like feed-forward networks and attention are used, and we aggregate local tokens through a learnable combination. For the global module, we enable each seed node to attend to a set of global tokens that represent centroids of all nodes in the graph. These centroids are updated during training using an exponential moving average k-means algorithm, providing a broader context beyond local neighborhoods. The final output representation for each node combines both local and global embeddings, processed through a feed-forward network. All components of the transformer include normalization and residual connections, and the combined representation is used for downstream predictions with task-specific loss functions. By integrating multi-element token representations in a hybrid local-global transformer architecture, RELGT effectively tackles the challenges of heterogeneity, temporal dynamics, and schema-defined structures in relational entity graphs. For our experiments, we evaluate RELGT on the Relational Deep Learning benchmark, which includes 7 datasets from various relational database domains, such as e-commerce and clinical records. These datasets vary in size, containing between 1.3K to 5.4 M records, totaling 47 M training records. We define multiple predictive tasks for each dataset, such as predicting user engagement with advertisements or clinical trial outcomes. Our evaluation focuses on 21 tasks related to entity classification and regression. In terms of setup, we implement RELGT within the RDL pipeline by replacing the original graph neural network component while maintaining the learning mechanisms and database loaders. Our model has between 10 to 20 million parameters, and we set a learning rate of 100,000. For tasks with fewer than 1 million training nodes, we adjust the number of layers and dropout rates, while for larger tasks, we fix the number of layers to 4. We use 300 local neighbors for sampling and set 4096 as the number of global centroids. We choose batch sizes of 256 for smaller datasets and 1024 for larger ones. Our aim is to demonstrate the advantages of RELGT over traditional graph neural networks without extensive hyperparameter tuning. We also compare our results with a hetero GNN baseline and 2 variants of the heterogeneous graph transformer to highlight the benefits of RELGT. Notably, many graph transformers are not suitable for heterogeneous graphs, which is why we use HGT in an enhanced version that includes Laplacian positional encodings computed on sampled subgraphs. Additional implementation details can be found in the appendix. Section Summary. In this section, we describe the RELGT model, which utilizes a transformer network with local and global attention mechanisms to effectively process relational entity graphs, capturing both fine-grained relationships and broader contextual information. We evaluate RELGT on the Relational Deep Learning Benchmark, RELBench, across various datasets and tasks, demonstrating its advantages over traditional GNNs and existing graph transformer models. Section: Results and Discussion. In this section, we present our results and discussion on the performance of RELGT compared to the standard GNN in RDL. Our experimental findings show that RELGT either matches or surpasses the GNN baseline across various datasets and tasks. We see the most significant improvements in REL trial site success, REL Avita ad center, and REL F1 driver top 3, while RELGT falls short on REL stack user badge by a small margin. For all other tasks, RELGT consistently performs better or at least equal to the GNN baseline. We believe this overall improvement stems from two main factors: the enhanced structural coverage provided by RELGT's attention mechanisms and the detailed encodings in our tokenization scheme. We also emphasize the critical role of the subgraph GNN in RELGT. Our ablation studies reveal that removing this component, which captures local subgraph structures, leads to a noticeable drop in performance across all tasks. This component is essential for clarifying parent-child relationships, especially when full attention is applied. Regarding the global module, our results indicate that its impact varies by task. For some tasks, like REL trial site success, removing the global attention leads to a significant performance decline, suggesting that the broader context is vital. Conversely, for tasks like REL Avita user clicks, removing the global module actually enhances performance, indicating that local information may suffice in some cases. Our ablation of other encodings shows mixed results. While eliminating certain fine-grained encodings can hurt performance on some tasks, it can improve it on others. This suggests that our current temporal encodings might introduce noise for tasks with specific temporal dependencies. Despite these variations, the full RELGT model consistently outperforms others when averaged across all tasks, indicating that further tuning of these components could enhance performance. We also note that HGT, a baseline for GT, generally underperforms compared to the hetero-GNN baseline, with only a few exceptions. The use of Laplacian eigenvectors in HGT improves performance in only a few tasks, and the computational demands for precomputing these features significantly increase runtime. Finally, we set the local context size at 300 nodes in our main experiments, but we explore its variability. While 300 nodes typically yield the best results, optimal sizes differ by task. For example, REL Avita ad center benefits from a larger context, while REL trial study outcome performs better with a smaller one. This suggests that task-specific tuning of the context size could further enhance RELGT's performance.